Hello everyone, this is Dr. Ali, and in this session we want to see how can we solve this knapsack problem using recursion method. But before we get to that part, that how this recursion, how can we formulate this problem as a recursion method. So first, look at this example that we have four items that I indexed them from 0 to 3, and each one of these items has a W and V, which W stands for weight and V stands for value. Okay, and we form this tree and we start from the root of, let's say, I0, which is the first item. Then we have two possible paths. Either we include that item in the knapsack or exclude. I show all the exclude parts from with blue and include parts with the red color. So for example, consider this path from root to this green circle. What it says? It says from I0 excluded. It means not put it in that knapsack. I1 excluded. I2 excluded. I3 excluded. Basically, we didn't pick anything. So when we don't pick anything, what's happening? What is the value in the knapsack? 0. So this definitely is 0. The value for this path is 0. There is nothing in the knapsack. So that's why I put here minimum possible value. We didn't pick anything, so the minimum possible value is 0. How about this path? We include everything. I0 is included, I1 is included, I2 is included, I3 is included. So what is the weight for this one? The summation of all the values is the value for this one, correct? So, and then the rest of these green circles, its value is something between 0 and the summation of all the values. But we are looking for the maximum possible maximum possible path or maximum green circle, which still satisfy that constraint that its weight shouldn't be more than the possible weight that the knapsack has. So this is the maximum value, but you cannot include everything in the knapsack, because if you could include everything, so this is a trivial solution. You didn't need to even solve it. We had a space for everything, so include everything. But now we know that you cannot include everything. So we want to see which one of these solutions are the right solution. Okay, so that's how we want to solve. But once we find out which one of these green circles are the one that we can achieve the goal that we have to maximize the value, at the same time we actually satisfy that constraint that not exceeding not exceeding the maximum value, that maximum weight that the knapsack can have. Then we can follow from that node to the root. For example, here, if this is the path that it gives us the maximum possible value, then we know that the I0 is not selected, item 1 is selected, item 2 is not selected, and item 3 is selected. Okay. So this is actually the how we want to attack this problem. We should have something to exclude and include an evaluation part. Okay. So let's look at the code. I define a function knapsack which gets in a space as a parameter. This space says that what is the available space in the knapsack at this moment. Weight and values, they are fixed. Weight is the actually vector of all the weights for items, and values is another vector as all the values for the items. Okay, and n is that item says that we want to evaluate. Should we include this item or should we exclude that item? Okay, and remember this, we have n item in our scenario, in our problem. For example, here n is 4, but remember the indexes are from 0 to 3. Okay, so here we say if the n is equal 0 or the space is less than 0. When n is 0 means there is no item. So of course, when there is no item, then it means the value that this knapsack has is 0. There is no value because there is no item to select from. Or when the space is 0 or negative, it means that there is no space left in the knapsack. So you cannot select anything new. So then we return 0. But what if the item that we want to evaluate, that should be include or exclude, has the weight above the possible weight? Then right away we know that this should be an exclude, because let's say I picked a laptop and I see there is 7 kilogram left in the knapsack, but the laptop has 10 kilogram. So what that means, it means that you shouldn't even consider including laptop to the knapsack, because its weight is already above this available space. So then if this is the case, then I call the knapsack with the same space, because we didn't include it in the knapsack. So it's the same space, weight and values are always the same. And then now we go toward the next item. That's why it says call the same function with n-1. So we go toward the next item. But what if the weights of that item that we want to evaluate is actually less than the space that's available? Then we have two paths, either included or excluded. If we exclude it, it's the exact same thing that I explained here, because we call the knapsack with the same space, weight, value, but we go toward the next item, okay? But if we include it in the knapsack, what happens is that, okay, we include it, so we need to add its value to the knapsack, because then it says its value of the item that we evaluate. Then you call the same function knapsack. Now the space of the knapsack should reduce as much as the weight of that item, because the item now is added to the knapsack. So the space of the available space should reduce by the weight of that item we included. The weight and the values, there are two vectors that are always fixed, and then we go toward the next item. So between these two include and exclude path, then we need to find the maximum. Which one is the maximum? If this, then we return the maximum value as the output for this knapsack. So if I run this for this number of items, it's like 10 items, then we select the maximum weight, and then we call this function, recursive function, with these values: maximum weight, actual weights, values, and the length of actually the number of items that we have. So we will see this in action in next session, that how's this working. And that's it for today. If there is any question or comment, please leave it down below, and stay tuned for the next upcoming sessions. Have a great day, everyone.